During the period of October 1957 through April 15, 1958, the Convair 880 commercial jet airliner began major component construction. Many subcontractors and vendors contributing parts and subassemblies from all over the country began making deliveries. The 880 program moved into full swing as the first production model of Convair's commercial jet airliner program was scheduled for test flights early in 1959. Significant in the period leading to this report was the construction of a complete metal mock-up in 880 tooling jigs. A metal mock-up that is being used to finalize all tubing, harness, and interior installations well ahead of production schedules. The swept-wing Convair 880 will be capable of operating from all airports throughout the world, now handling 4-engine piston aircraft. The ruggedly built Convair 880 was specifically designed for economical medium and short-range operation. But with the addition of the wing center section fuel system, it converts to a highly efficient long-range liner. In any range, the 880 is designed to provide the finest in passenger and operational services. 2 plug-type doors are located at each end of the fuselage for easier passenger handling. Opening or closing can be accomplished by the stewardess with a minimum effort. When the door is pulled to the fuselage, it slides downward and wedges into place and is safely secured in one simple motion. The interior features unique appointments in every detail of comfort and convenience. Standard seating arrangements will accommodate 88 passengers in luxury flights and 109 in the coach configuration. An airline crew can convert first class to coach in a few hours. The high safety qualities incorporated in the new dual window arrangement offer each passenger his own private viewing area. The 880 air conditioning system was developed and tested as a part of the 880 test program. 44 general outlets, along with 109 individual passenger outlets, supply a complete change of fresh temperature-controlled air every 2½ minutes in the passenger area and every minute in the smaller flight deck spaces. The 2 galleys have been compactly designed for efficient service. The spaciousness of the 880 cabin allows for more comfortable passenger seating arrangements than ever before possible. The advanced designs in 880 cockpit lighting eliminate distracting reflections and keep the instruments in the cockpit area glare-free. The glare shield keeps the windshield free from instrument panel reflections. White and red dimmable floodlights are used to eliminate the tunnel effect created by the shield. Similar floodlighting is available throughout the cockpit. The new use of printed circuitry makes each panel more compact and increases the effectiveness of the new improved dimmable edge lighting. The lighting designs incorporated in the flight engineer's panel simplify the operation of the 880's systems. In the newly constructed Convair Acoustics Laboratory, extensive sound testing has been conducted to determine the best material to be used in soundproofing the 880 cabin. The material to be tested is installed in the window separating a live room from the completely soundproofed room on the other side. In the adjoining soundproofed room, sound readings are taken. Over 100 materials have been tested in this way to determine the best possible soundproofing material to be used in subduing jet engine and aerodynamic sounds in the cabin area. On the outside of the metal fuselage section here in the large reverberation room, sound levels simulating the noise produced by the 880 engines have been established. Acoustic tests are first conducted on the bare metal fuselage section, and then different layers of soundproofing materials are added in a series of build-ups with tests in each stage. This is continued until a full-scale cabin mock-up has been completed and tested. Then furnishings are removed, testing is completed, and a final soundproof configuration established. In the General Electric plant in Evandale, Ohio, the CV-880 engines, 4 of which power the 880, are being manufactured. The military version of this engine is being used in the Convair-built B-58 Hustler, the world's fastest bomber. The Minnesota Mining and Manufacturing Company in St. Paul, Minnesota, contributed to the success of the Convair-developed manufacturing process called Scotch weld. This is a process that combines added structural strength with a greater fuel tank integrity, making possible the maintenance-free integral fuel tank. This design permits the use of the interspar box structure as a fuel container and gives maximum range with minimum maintenance. The Scotch weld tank has not developed a single case of fuel leakage in over 4 years of rugged military use in hundreds of F-102 and F-106 interceptors. The Scotch weld process begins in the cleaning baths built especially for the construction of the 880 at a cost of over $500,000. In the cleaning bath area, the parts to be Scotch welded are cleaned, chemically treated in special tanks, oven dried, Scotch weld primed, and force dried in the curing oven. In the assembly area, the Scotch weld adhesive film with its protective backing is applied over the drilled sections where metal is to be joined to metal and drilled to match the holes in the metal sections to be assembled. The protective backing is then pulled away, leaving the translucent Scotch weld film in place. And the fuel-tight rivets are driven. The completed wing assemblies are brought to the giant 880 oven built especially for final 880 wing curing. The $175,000 oven installation was thoroughly tested using a pair of R3Y wings similar in size to those of the Jetliner. Once the oven curing is completed, the wings are ready for mating. At Convair's structural test jig, the Scotch weld system is once again tested in an 880 wing section. The purpose is to demonstrate the fuel-tight integrity of the Scotch weld integral wing fuel tank by load cycling under pressure and adverse temperature conditions. Testing is done at temperatures ranging from 65 degrees Fahrenheit below zero to 160 degrees Fahrenheit above. Internal pressures range from 3 to 10 pounds per square inch. External load cycling pressures exceed 13,000 pounds. Medium-range transport aircraft are subjected to more strenuous punishment than long-range transports. And these highly successful tests have subjected the 880 wing to stresses far in excess of those that will be encountered in normal operation. No fuel leaks have occurred in any test conducted. The last of the famous Convair 440 liners in service throughout the world reached the end of their assembly line as the earlier phases of the 880 tooling program began. With the completion of the highly successful Convair liner program, over 1 million square feet of floor space became available for the production of 880s. The near-sonic speeds of the 880 require a higher degree of precision construction than ever necessary in the slower commercial airliners of the piston era. Pioneered by Convair in supersonic F-102 and F-106 interceptor construction, optically aligned tooling jigs are used to build the 880. A revolutionary new tooling method that makes possible the highest degree of accuracy in aircraft precision construction to date. Optical tooling means simply that large fixtures are constructed along lines and angles that are established optically. From this basic principle, a jig big enough to assemble a complete 880 wing can be aligned for construction. An alignment telescope is precision mounted on one end of the jig. An illuminated target is precision mounted on the opposite end of the jig. Facility gauges or locators are added in which bullseye targets can be inserted and positioned in strategic locations along the frame to be aligned optically so that a basic precision line of sight is established on which the wing buck will be built. This fundamental procedure is continued through all necessary angles until the tooling jig is completely aligned, and on which an 880 wing can be assembled with precision accuracy. Periodic checks are made to ensure that the jig remains true, and construction becomes a matter of basically clamping parts to the pattern and riveting them until the wing is finished. Approximately 30,000 structural parts needed for a single 880 are meeting regular production schedules. Cover plates, forgings, channels, sump castings, landing gear mechanisms, ducts, fuselage skins. The world's largest radial draw former, built to Convair specifications at a cost of $800,000, is one of the many special installations added to the 880 production line. A tremendous pressure of 75 tons is applied by the draw forming machine to raw stock, and in a single movement, one of the huge fuselage belt frame sections is formed and ready for assembly. In the Spar Mill area, 3 different size spar mills are being used in the manufacture of 880 wing spars. A 30-foot mill, a 66-foot mill, and the 108-foot Onsrud, installed for milling the larger 880 wing spars. The spar rails are fitted to optically aligned jigs on the spar tables, and webs and stiffeners are added, drilled on the new automatic gantry-mounted drill, and riveted. The individual spar sections are then moved to the optically aligned vertical tooling jigs, where the 2 sections making up a completed spar are joined and the pylon fittings added. When the spar has been completed in the vertical jigs, it is ready for the major wing assembly. In the wing skin and stringer panel optically aligned jigs, the wing panel sections are being constructed. The stringers are fitted and clamped to the tooling pattern. The wing skins are then lowered to the tooling jig and fitted to the stringers, and riveted, and the wing panel is completed. In production areas throughout Convair San Diego Plant 1, the major components of the 880 are now meeting production schedules. From the earliest test stages through more advanced testing, the 880 has moved steadily toward full-scale production. Huge equipment installations have been designed and installed. The thousands of small parts used in the liner are meeting weekly production schedules. The first flying version of the 880 is now under construction and will be the first of a full-scale production program aimed at producing 6 Convair jetliners each month. The 880 has grown from an idea into production and is moving steadily toward the first test flights scheduled for early in 1959. Here now is Mr. Sandy Cogan, Convair Vice President and San Diego Division Manager.
What you have just seen represents the progress we here at Convair have made in developing a commercial transport that will answer the needs of airlines for many years to come. In the past, we have shown you the extensive test and development programs that have been in progress for over a year. Now you have seen the immense production program currently producing the 880 jet airliner. From this beginning, 880 manufacture is moving toward a full-scale program capable of supplying airlines all over the world with Convair jet airliners beginning early in 1960. Able to land in over 335 cities throughout the United States, Canada, and Hawaii, the 880 is the only airplane initially designed for the rugged demands of medium-range service. Typical of some of the routes the 880 can service: Chicago to Kansas City, 405 miles. Kansas City to Los Angeles, 1,368 miles. Los Angeles to Seattle, 964 miles. And of course, cross-country, San Francisco to New York, non-stop, a distance of 2,580 miles. Although designed for medium-range service, the versatile 880 will economically fly routes as short as 250 miles, or with the addition of the wing's center section fuel system, non-stop routes as long as 3,250 miles. This means that the 880, purchased for medium-range work, can be used by an airline to supplement larger jets on long-range flights, and it will do so at less than two-thirds the cost involved in operating the larger ships. The extra speed, combined with the fact that it is the only jet transport initially designed to operate economically with a deluxe four-abreast seating arrangement, virtually assures that passengers will prefer to fly in the 880. The 880 will fly 615 miles per hour, making it the world's fastest airliner, faster than any competing jet transport by a substantial margin. This extra speed, combined with a turnaround period of only 25 minutes, gives the 880 an excellent work capacity. For instance, the 880 cuts almost 40% off the time required for current aircraft to make the trip from Chicago to Los Angeles. The trip now requires 5 hours and 24 minutes. The 880 will fly it in 3 hours and 25 minutes. This speed advantage and the rugged construction of the 880 means longer first-line life than has ever been realized in the past with piston engine aircraft. It will be first-line equipment for at least 12 to 15 years, and in some cases, as much as 20 years service will be realized on the routes for which it was initially purchased. On a 1,000-mile trip, the 880 need carry only 34 passengers to cover the total cost of operation. Conservatively then, a 60% annual load factor on a 1,000-mile run, such as New York to Miami, would earn an airline $2,125,000 a year, based on a 10-year depreciation. Forecasts show that airline traffic in the U.S. will more than double by 1965. Traffic that will require jets like the 880. Convair is proud to announce that the tempo of production is increasing daily. The first 880 will fly early in 1959, and we at Convair are confident that the 880 will be the finest and safest in jet air travel.
This is the Convair 880 commercial jet airliner. More than 4 years have been devoted to developing and proving the 880 to make it the finest and safest modern jet transport possible. From 880 assembly lines now producing on a regular production schedule, 4 880 aircraft were specifically assigned to the test programs. 3 of these aircraft have been flying on regular test schedules. The other was assigned to ground tests here in the structural test facility. Its task was to demonstrate 880 ability to withstand the maximum flight loads it was designed to take. Rigged in these elaborate whiffletree arrangements, the aircraft was deliberately twisted and bent in a series of instrumented tests. Tests that were designed specifically to explore maximum design loads in a program that simulated all operational extremes of flight through all types of weather. During these investigations, hard landings were simulated up to design limit loads. Engine pods and pylons were tested to extremes to simulate side gust loading, such as would be encountered in rough, stormy air. The fuselage was pressurized and deliberately deflected with massive loads to prove its ability to withstand forces that might be encountered during a pullout, such as would result from an abnormally steep dive. Typical of the tests conducted on the aircraft were those accomplished in the vertical tail areas. Diametrically opposed loads were used in a torsion test that applied maximum loads to the vertical fin in one constant direction, while at the same time, opposite loads were applied to the rudder. A test that explored strains that could be encountered during an engine-out condition. In tail fin bending tests, loads of up to 32,000 pounds were used to bend the vertical fin 15 inches off-center. A test designed to simulate maximum side gust loading conditions. Critical wing deflection tests were undertaken to simulate maximum wing loading, like the strains that could be encountered in a severe stall or pull-out maneuver. During this test, the wings were deflected as much as 6 feet, with loads ranging as high as 160,000 pounds. Downward deflection of the nose area was in excess of 1 inch, with over 43,000 pounds of load in this area. Aft section loading was 100,000 pounds, with a total downward deflection on the section of only 8 inches. The aircraft returned to normal following these maximum loads with no problems encountered. In each phase of the test program, the airplane was fully instrumented and results recorded for complete evaluation. The aircraft was engineered to exceed these test limits by 1.5 times the maximum design loads applied without sustaining any major structural failure. On assembly lines now producing 880s for delivery to airlines, an 880 was constructed to undergo an exhaustive fatigue cycling demonstration. It was installed in a special tank measuring 110 feet long by 20 feet wide. When filled to capacity for the test, the tank contains nearly 400,000 gallons of fresh water. In the investigation currently in progress and scheduled to cover more than a year, the fuselage will be continuously cycled underwater in a test that will simulate more than 20 years of first-line service operation. A system of hydraulic actuators are used to apply the strains that would be encountered during actual ground or in-flight operation of the aircraft. The fuselage was constructed complete with stub wings. Addition of the wings permitted full-scale examination of the fuselage, including strains produced in the wing root area. This is the first time that the combined fuselage and wing section of a commercial jet aircraft have been fatigue tested this extensively in the United States. The test is being run on a weekly basis. Approximately 5,000 cycles are completed each week. The tank is then drained for a thorough inspection and refilled for continuation of testing. Control of the test and recording of data is done in a structure adjacent to the tank. Here, through an electronic time-controlled cycle program, the fuselage is automatically put through a complete landing, taxi, and flight cycle each minute. Each 1 minute cycle simulates 1 hour of actual flight time. During the cycle, the fuselage is pressurized from 0 to 8.6 pounds per square inch internal pressure, well in excess of maximum in-flight operation pressures, and then back to 0 again. Stresses applied to the aircraft during various stages of cycling range from 1.22 to 1.85 times the pull of gravity. Daily inspections are made by specially trained crews of divers to ensure that no trouble could go undetected at any time. As a result of these tests, airlines purchasing the 880 will be furnished with inspection manuals that will contain information on the tests and serve as a guide for routine inspections for the life of the aircraft, in addition to ensuring that the aircraft will maintain its airworthiness serviceability through a full first-line lifespan of 20 years. More than 400 in-flight test hours have been completed by the 3 test 880 jet airliners involved in the program. The availability of these aircraft to meet flight schedules has been the best of any aircraft ever tested at Convair. 3 and 4 engine minimum takeoff performance and maximum effort landing investigations were conducted at the Air Force Flight Test Center at Edwards Air Force Base, California. These tests were conducted to determine takeoff capabilities at various weights and required runway lengths using both 3 and 4 engines. Minimum landing distances and rejected takeoff distances were also established. Over 200 stalls were completed in the program to determine slow-speed flying characteristics in varied configurations. Fuel jettison on the 880 is accomplished through 4 fuel nozzles located in pairs near the aft tip edge of each wing. The nozzles eliminate the customary extendable dump chute. They are permanently fixed with no moving parts and no maintenance requirements. The pattern is such that fuel can be jettisoned at all speeds without impinging any of the aircraft surfaces. Flow rates for the system were established as being well above those required. It is able to dump 51,700 pounds in a period of 20 minutes, 65% faster than minimum requirements. Each of the 3 test aircraft is specifically instrumented for the particular group of tests being conducted during any given flight. Basic data receiving equipment includes an airborne tape recorder for permanent record and a direct reading oscillograph. 2 photo panels containing all instruments pertinent to the test. A temperature recorder automatically keeps a record of temperatures in all areas of the ship throughout the entire flight. During flutter tests, telemetering is used. In these investigations, the pilot contacts the facility and initiates the test event by means of a countdown. All flutter flight activities are monitored here in the telemetering facility. Once a test has been initiated by the pilot, data is transmitted as it is produced on the aircraft to recorders capable of handling 20 separate data functions at one time. In addition to the permanent record, discriminators break the incoming RF frequencies into voltages that are graphically interpreted in visual form for an immediate quick look evaluation. With the test satisfactorily completed and tabulated, clearance is then given by the facility to the aircraft to continue to the next checkpoint. both here in San Diego and at the Edwards Flight Test Facility, extensive testing was done on the thrust reverser system developed jointly by Convair and General Electric for the CJ-805-3 engines that power the 880. Over 100 taxi runs were made to establish cascade settings that would achieve optimum efficiency. During all test flights completed by the 3 880 test aircraft to date, no engine changes have been made as a result of engine failure. The 880 is now leaving production lines on regular schedules, ready for delivery. During the test program, it has proven its ability to land and take off well within performance predicted limits, and in level flights has more than met speed performance guarantees by demonstrating its ability to fly at its optimum estimated speed of 615 miles per hour. All Convair testing has been concluded, and emphasis is now shifting to final Federal Aviation Administration certification testing. Certification will be completed by spring 1960, with first deliveries beginning in November of 1959 to Transworld and Delta Airlines. This then is the Convair 880, the world's fastest jet airliner. Structurally and performance proven, luxuriously appointed, versatile, the most advanced jet airliner available to the flying public today.